Bayesian deep learning and a probabilistic perspective of generalization is the headline of an article written by Andrew Gordon Wilson and Pavel Ismailov from New York University. Hello everyone, this is Nima. For this presentation, I will start with a brief overview on abstract of the article. Then I will talk about uncertainty and Bayesian methods. Also, I will explain about marginalization. I will briefly talk about SWA, which stands for Stochastic Weight Averaging, and SWAG, which is SWA in Gaussian modes. Then I will present double descent issue, and then I will show some test results on comparison and end the presentation with a conclusion. The abstract of the article reveals different key points and focus area of the work. I highlighted them in yellow, and these are 1. The key distinguishing property of a Bayesian approach is marginalization, rather than using a single setting of weights. Bayesian marginalization can particularly improve the accuracy and calibration of modern deep neural networks, which are typically underspecified by the data and can represent many compelling but different solutions. 2. They explain results that have been presented as mysterious and distinct to neural network generalization, such as the ability to fit images with random labels. And 3. Bayesian model averaging alleviates double descent. Before going ahead, we have to have a look at uncertainty. Uncertainty. What is it? Well, ultimately, machine learning models are used to make decisions. Representing uncertainty is crucial for decision-making process. For instance, in medical diagnosis and autonomous vehicles, we want to protect against rare but costly mistakes. Deep learning models typically lack a representation of uncertainty and provide overconfident and miscalibrated predictions. The uncertainty in neural networks can generally be classified into two groups. One is data uncertainty, and two is model form uncertainty. The data uncertainty relies on the probability distribution of a dataset, which may be associated with the inherent noise in the data generation or observation processes. Therefore, this uncertainty is irreducible. The second category of uncertainty is model form, which is due to the lack of confidence in making a prediction by a specific model. From the context of neural networks, this uncertainty may be reduced by generating more representative training data. One of the well-known methods to assess model form uncertainty is the use of Bayesian neural networks, which are BNNs. BNNs assume each trainable parameters of a neural network to be sampled from joint distribution of all parameters that is conditioned on the training data. By characterizing the trained weights and biases of a neural network with a density, several forward model evaluations may be made for the same set of inputs that are used for generating ensemble statistics, such as mean and confidence intervals for the target variable. And here I would like to mention some key terms that are required before going ahead with this presentation. The first one is prior. What is it? It is a probability distribution representing knowledge or uncertainty of data object prior or before observing it. The second one is likelihood. Likelihood is the probability of falling under a specific category or class. And the last one is posterior. Conditional probability distribution representing what parameters are likely after observing the data object. Posterior is equal to a multiplication of prior to likelihood. And there is an equation for posterior where the probability of theta given y can be calculated in this way. Bayesian methods. The Bayesian approach defines a full probability distribution over parameters instead of a parameter point estimate. This is called the posterior distribution. The posterior represents likelihood, hypothesis, or uncertainty about the value of each parameter, and Bayes' theorem is used to compute the posterior using the following equation that is shown on this screen. Bayesian neural networks which learn a distribution over verse are currently a state of the art for estimating predictive uncertainty. The Bayesian approach assigns probabilities to hypotheses, unlike frequentist approach that assigns probabilities to data. Bayesian deep learning has been making fast practical advances with approaches that now enable better accuracy and calibration over standard training with minimal overhead. There are different Bayesian methods. The first one is named as Markov chain Monte Carlo. Monte Carlo was at one time a gold standard for inference with neural networks. However, it requires full gradients, which is computationally intractable for modern neural networks. The second one is variational inference. It was suggested for fitting a Gaussian variation posterior approximation over the weights of neural networks. The technique was generalized by Kingma and Welling, two persons, which proposed the reparameterization trick for training deep latent variable models. Multiple variation inference methods based on the reparameterization tree were proposed for deep neural networks. While variational methods achieve strong performance for moderately sized networks, they are empirically noted to be difficult to train on larger architectures such as deep residual networks. The third one is dropout variational inference. A spike and a slab variation distribution were used to view dropout at test time as approximate variational Bayesian inference. Concurrent dropout extends the idea to optimize the dropout probability as well. From a practical perspective, these approaches are quite appealing as they only require ensampling dropout predictions at test time, and they were successfully applied to several downstream tasks. And last but not least is the Laplace approximation. It was notably used for Bayesian neural networks, where a diagonal approximation was utilized for computational reasons. Later on, diagonal Laplace approximation was proposed to overcome catastrophic forgetting in deep learning. More recently, the use of either a diagonal or KFAC approximation to the Hessian matrix for Laplace approximation was proposed. Inductive bias. Every machine learning model requires some type of architecture design and possibly some initial assumptions about the data we want to analyze. Generally, every building block and every belief that we make about the data is a form of inductive bias. Inductive bias in Bayesian models shows itself in the form of the period distribution that we choose for the variables. Consequently, the period can shape the posterior distribution in a way that the latter, which is posterior, can turn out to be a similar distribution to the former, which is period. Inductive biases play an important role in the ability of machine learning models to generalize to the unseen data. A strong inductive bias can lead our model to converge to the global optimum. On the other hand, a weak inductive bias can cause the model to find only the local optima and be greatly affected by random changes in the initial states. Inductive biases are categorized into two different groups called relational and non-relational. The former represents the relationship between entities in the network, while the latter is a set of techniques that further constrains the learning algorithm. Generalization. An important question in the introduction of the article is how and why neural networks generalize. The authors argue that from a probabilistic perspective, generalization depends largely on two properties: the support and the inductive biases of a model. So we can summarize that generalization is the support and inductive bias that are two important parameters of it. We often use neural networks with millions of parameters to fit datasets with thousands of points. Furthermore, non-parametric methods such as Gaussian processes often involve infinitely many parameters, enabling the flexibility for universal approximation. Yet in many cases, provide very simple predictive distributions. From a probabilistic perspective, generalization depends largely on these two parameters or these two properties, the support and the inductive bias of a model. Well, there is a note also that parameter counting, only parameter counting, is a poor proxy for understanding generalization behavior. Support is the range of dataset classes that a model can support. In other words, the range of functions a model can represent, where a function is trying to represent a data generative process. And the inductive bias that we already talked about defines how good a model class is at fitting a specific dataset class, for instance, images, text, or numerical features. And then the following is the marginal likelihood or the evidence equation. Marginalization. The process of producing a distribution over a single variable or a subset of variables from a larger set of variables without any reference to an observed set of variables. Marginalization is a method that requires summing over the possible values of one variable to determine the marginal contribution of another. Bayesian marginalization can particularly improve the accuracy and calibration of modern deep neural networks, which are typically underspecified by the data and can represent many compelling but different solutions. In our case, marginalization is a posterior weighted model average. Rather than bet everything on one hypothesis with a single setting of parameters W, we want to use all settings of parameters, weighted by the posterior probabilities. The procedure is called marginalization of parameters, as the predictive distribution of interest no longer conditions on the parameters. So the key distinguishing property of a Bayesian approach is marginalization. And then we have the equation of the BMA, Bayesian model average, for which X is the input, could be spatial locations, images, and the Y is the output, could be regression values, class labels, and W are the weights or parameters, and the D is data. The authors stress that the key distinguishing property of a Bayesian approach is marginalization instead of optimization, where we represent solutions given by all settings of parameters weighted by their posterior probabilities, rather than bet everything on a single setting of parameters. This is very important to remember. And here we have a probabilistic perspective of generalization that is represented by a figure in the article. In section A, we have different models here. On a horizontal axis, we have a conceptualization of all possible datasets. And on the vertical axis, the bias and evidence likelihood for a model. Well, the green one is a well-specified model with calibrated inductive biases, and the example for it would be a CNN. The purple one, it's a simple model with poor inductive bias. An example could be a linear function. And the pink one, it could be a complex model with poor inductive biases. An example could be MLP. So the purple and the pink could be somehow the opposite of each other. One of them is the simple model, and the other one is the complex model. But both of them are suffering from poor inductive biases. And ideally, a model supports a wide range of datasets, but with inductive biases that provide high prior probability to a particular class of problems being considered. Here, the CNN is preferred over the linear model and the fully connected MLP for CIFAR 10. Section B shows that by representing a large hypothesis space, a model can contract around a true solution, which in the real world is often very sophisticated. Section C shows that with truncated support, so if the support is not good enough, a model will converge to an erroneous solution. And section D, which is related to this complex model with poor inductive bias, is showing that even if the hypothesis space contains the truths, a model will not efficiently contract unless it also has reasonable inductive biases. Stochastic weight averaging, or SWA. It addresses weights uncertainty in a model by recording the weights during training and then taking their average. The result is better generalization. When it comes to training of the SWA, we can see that compared to a normal testing that we load the weights and it goes through a model and then the prediction will be done through a predictor, in SWA testing we load the means of the weights and then perform batch normalization statistics update on that, and then it will go through a model and then through the prediction process. So for the model training, we start collecting weights at every epoch, and then we average them at each collection point. As you can see through this equation, that the weights are averaged at each collection point that we are taking them. N is the number of collections, and I is the number of the epoch at which we are taking and then we are averaging them. SWAG, a stochastic weight averaging Gaussian, is a state-of-the-art model form uncertainty qualification technique founded on the concept of stochastic weight averaging, or SWA. It's a simple, scalable, and convenient approach to uncertainty estimation and calibration in Bayesian deep learning that approximates the posterior distribution of the collected weights as a Gaussian distribution, conditioned on the training data. By sampling the weights from the distribution and performing an ensemble estimation, both the target estimation and their standard deviation can be obtained. It estimates the first and the second moments of the iterates to construct a Gaussian distribution over the weights. So similar to SWA, but aims to fit a Gaussian distribution over the weights. So we use the SWA solution as mean, then a low rank plus diagonal covariance derived from the weights and sample weights from distribution to create a new model. When it comes to training of SWAG, compared to a normal testing that we saw previously, that we load the weights and it goes through a model and the prediction process, in the SWAG, we sample the weights with a scale S from each weight and then perform batch normalization statistics updates. So we start collecting weights at every epoch and then compute a k-rank deviation matrix by appending at each collection point and then removing the columns when rank is attained, then compute at the end of the training. So SWAG samples several weights during a neural network training to obtain ensemble prediction. And by using a SWAG, we have some advantages. It improves model deterministic skills compared to classical training without additional computational costs. Approach deterministic and probabilistic skills at deep ensemble at a fraction of the cost. Transform a deterministic model into a stochastic one. Allows to generate large ensemble predictions at a tiny fraction of the current cost involved in training many models. Empirically, SWAG performs on par or better than popular alternatives including MC dropout, KFSD Laplace, and temperature scaling on uncertainty qualification, out of distribution detection, calibration, and transfer learning in computer vision tasks. and we have oh sorry we have oops. And we have MultiSwag, which combines the two models of approximating a posterior within a single basin of attraction with deep ensembling approach. It's a method inspired by deep ensembles, which marginalizes with basins of attraction, achieving improved performance with a similar training time. Most Bayesian deep learning methods instead focus on approximating a posterior within a single basin of attraction. MultiSwag combines it with deep ensembling approach. Therefore, MultiSwag combines multiple independently trained swag approximations to create a mixture of Gaussian approximations to the posterior, with each Gaussian centered on a different basin of attraction. Here we have a likelihood comparison between multi-SWA, multi-swag, and deep ensembles, using a pre-ResNet 20 on Cypher 10 with varying intensity of Gaussian Blur corruption. Well, in short, deep ensembles is a combination of two models to obtain a more powerful model. While the training time for MultiSwag is the same as for deep ensembles, at test time, MultiSwag is more expensive, as the corresponding ensembles consist of a large number of models. MultiSwag outperforms deep ensembles significantly on highly corrupted data. The image in each plot, from left to right, shows the intensity of corruption. For all levels of intensity, MultiSwag and multi-SWA outperform deep ensembles for a small number of independent models. For high level of corruption, MultiSwag significantly outperforms other methods even for many independent models. For lower levels of corruption, MultiSwag works particularly well when only a small number of independently trained models are available. Multi-SWA also outperforms deep ensembles and has the same computational requirements at training and test time as deep ensembles. Conventional wisdom in statistics is that larger models are worse, which is shown by this bias variance trade-off curve on the right side of the screen. As we increase the capacity of hypothesis class H, for instance, as we make our model more complex, the model overfits and the training data, therefore, uh, the training risk error reaches zero. Test risk error also follows the same trend until we reach the sweet spot, which describes the best model for our use case. After this point, the test risk increases. If H is too small, then all predictors may underfit and predict poorly on new data. If H is too large, all predictors may overfit, and then we have poor accuracy on new examples. We see that practitioners use larger and larger neural networks to improve tested accuracy, and on this curve, after a certain point of overfitting, it's found that the test risk again starts to decrease. This phenomenon is called as double descent. Double descent describes generalization error that decreases, increases, and then again decreases with increase in model flexibility. The first decrease and then increase is referred to as classical regime, which are models with increasing flexibility that are increasingly able to capture a structure and perform better until they begin to overfit. The next regime is referred to as the mother interpolating regime, which has been presented as mysterious generalization behavior in deep learning. Here is a comparison that others presented between SGD, SWAG, and MultiSwag, and showing how MultiSwag alleviates the double descent issue through ResNet 18 on Cypher 100. Section A shows test error with true labels. And we can clearly see that how MultiSwag is performing compared to the other ones. Section B shows a negative likelihood loss with true labels, with varying width on cipher 100. Section C shows test error when 20% of the labels are randomly reshuffled to add some noise. So this is somehow a corrupted data. And section D shows negative likelihood when 20% of the labels are randomly reshuffled. Again, the corrupted data. So, and to have noises here. And again, we can see that how MultiSwag, the green line, is performing compared to Swag and SGD here. Swag reduces double descent, and MultiSwag, which marginalizes over multiple modes, entirely alleviates double descent, both on the original labels and on their noise labels, both in accuracy and negative likelihood. Section E shows the test errors for MultiSwag. With varying number of independent swag models, error monolithically decreases with increased number of independent models, alleviating double descent. MultiSwag also provides significant performance improvements. The performance of MultiSwag solutions increases monotonically with the size of the model, showing no double descent even under significant label corruption. The results highlight the importance of marginalization over multiple models of the posterior. Under 20% of label corruption, swag clearly suffers from double descent, while multiswag does not. In section E, it is shown how the double descent is alleviated with increased number of independent modes marginalized in multiswag. The results also clearly show that MultiSwag provides significant improvements in accuracy over both SGD and SWAG models, in addition to negative likelihood. This is an often overlooked advantage of Bayesian model averaging. In conclusion, we have the key distinguishing property of a Bayesian approach is marginalization, rather than using a single setting of weights. Bayesian marginalization can particularly improve the accuracy and calibration of modern deep neural networks, which are typically underspecified by the data and can represent many compelling but different solutions. Generalization depends on the support and inductive bias of the model. The support should be as large as possible, and inductive biases must be well calibrated to a given problem class. Bayesian neural networks can also be far more robust to noise, as shown in double descent. Multimodal marginalization in MultiSwag can entirely alleviate double descent. MultiSwag provides significant improvements in both accuracy and negative likelihood over SGD, SWA, and SWAG training and unimodal marginalization. Thanks for your listening and for your attention to this presentation. I have also presented a list of my references when I was reading this article, that you can find them here if you're interested to read more on some of those terms and those work-related topics. And have a good day.